Before the break, we did one-dimensional collisions where we did conservation of momentum. In fact, we just wrote a quiz on that with 3 questions. Questions could have looked something like this. Object number 1 moving towards a stationary object number 2. Let's say they collide with each other, they stick together for whatever reason, and they head off as one. We can deal with this, right? We just did deal with this 3 times on the quiz that we just wrote. We say for this PI is equal to PF. We would say M1 V1I plus, what's the momentum of object number 2 here before the collision takes place? 0, because object number 2 is at rest. Equals, now if they stick together, we're going to say M total, MT, times VF. If they bounce apart, then we'll make it M1 V1F plus M2 V2F. Let's say they stick together though. We solve for VF and we get a certain value. Can't put a number down here because we don't have any numbers in the question, but we would be able to solve for that given numbers in this situation. Now, another situation, this time object number 1 is at rest, and object number 2 is moving downwards towards it with a certain velocity. For this one as well, we'd say PI is equal to PF. The momentum of object number 1 here is, what's the momentum of object number 1 in this question? 0, because its velocity is 0. So we'd say 0 plus M2 V2I equals, well, assuming they stick together, we'd say M total times VF. We'd solve for VF again here, and we're done. All right, we've solved for the final velocity of the 2-ball wreckage in the first question. We've solved for the final velocity of the 2-ball wreckage in the second question. 2 questions, independent of one another. We can do both of those. You guys took a quick little look at your quiz answers, and it looks like you guys did really well on your one-dimensional collision quiz. So you guys could easily, I think, do these 2 questions. Now, what happens when we come across this situation? We looked at this just before the break. Object number 1 moving this way. Object number 2 moving this way. They collide with each other. They stick together again. They're going to head off as one somewhere down here, somewhere down and to the right. How do we analyze this? Well, the same way. For the x component, we would do this. The x component is PI is equal to PF, M1 V1I plus 0. Why is object number 2 0 for this question? Object number 2 looks to be moving to me. It's moving downwards or moving to the south. Why are we calling it 0? Yep, Jack. Good. We're analyzing, in this case, the x-axis. That's this, right? How much of that object number 2 is on the x-axis? 0. None of it. So its momentum on the x-axis is 0. We would solve for VF there, just the same as we did right up there. And then we would do the y component. For the y component, we would use this. Why is object number 1 0 for the y component? Yeah? Good. We're looking at the y-axis now, which is this. And how much of that object number 1 is on the vertical axis? None of it. Yeah, all of the second one is on the y-axis, but none of object number 1 is. So we'd solve for VF there, just the same as we did, just the same as we would have done up here. Now what? You got a VF, x component, which is exactly the same as the first question on the board, and a VF for the y component, which is exactly the same as the second question on the board. We got 2 VFs. We don't want 2 VFs. We want 1 VF. We want the red one here. How do we get it? Now comes the physics 20 part, right, Jack? Yeah. Your horizontal VF, which is going to end up being to the right, a positive value if you actually solve for it, and your vertical VF, which would turn out to be a negative value if you actually solve for it. And then you would combine them. And I would just solve for that value of VF. This is like, well, the mechanics of this is physics 20, but the math is actually math 10. How would you solve for the hypotenuse given x and given y? Oh, come on, you so know this. Let me give you a hint. Let me give you a hint. Let's call this A. Let's call this B. How would you solve for C, the red side, given A and B? Good. It's the square root of A squared plus B squared. The Pythagorean theorem, right? I don't care if you even remember the name of it, as long as you can do it. The square root of A squared plus B squared. And theta, which is our angle there, we have to solve for that because it is a vector, would be the inverse tan function of opposite over adjacent. So that would be B over A, or the y-axis over the x-axis. Now, let's say I got an angle of 40 degrees there. What would I say? 40 degrees what of what? This is east. This is south. We're going south and east, right? Is it 40 degrees south of east or 40 degrees east of south? The way that I have it drawn there. Yeah, I'm measuring my angle from the east, right? Like clearly it's not measured from the north or the west. It's in the southeast direction. Where's my angle measured from? It's measured from the east. South from the east, right? South from east or south of east. So we'd say that would be 40 degrees south of east. Does that make sense? Good? All right. You guys can do this, right? Hey, if you can do this, and you can do this, and you can do this, then you can do this problem where car number 1 is colliding at 90 degrees with car number 2. What about this? What about this situation here? This is a little bit new. Not entirely, because really every little part of this question you've already done. It's just a matter of putting a few things together. What about this situation where you've got this fireworks bundle sitting on a table? We'll just say it's sitting right here on a table at rest. Suppose it into 3 pieces. First piece goes north at 120 meters per second. We're going to call that object number 1. I'm going to say its mass is 120 kilograms, and its velocity is 120 meters per second. Second piece goes at 30 degrees south of east. We'll call that piece number 2. Its velocity is 100 meters per second, and its mass is 1.10 kilograms. There's a third piece. Where do you think the third piece is going to go? Take a guess. An educated guess, though. It's going to go right or left? East or west? You're being really specific there. Let's hold off on being that specific, okay? And let's just give the general vicinity, okay? Are we going to go, we got an object that's going up, and we have an object that's going south and east. Is the third object going to go east somewhere or west somewhere? There was 0 momentum before this explosion occurred, right? There's 0 momentum after this explosion occurs. If something goes to the east, plus 5, then something else must go to the west at negative 5 in order to give me a total momentum of 0. Does that make sense? So it's going to go to the left. Now, up and to the left or down and to the left, don't really know about that. Don't really know about that. The left counters the right. But there's already an up and a down. So what am I trying to counter there? I'm not sure. I'm guessing down and to the left, but it could be up and to the left. We're not sure. In the end, the resultant that you're trying to find here, it's not critical that you have that drawn correctly. It just helps us to visualize it a little bit better if you do have it drawn correctly. What's the mass of the third piece? Do we know that? Yeah, how'd you know that? Yeah. The mass of the fireworks bundle was 3 kilograms. We're going to say 3 minus 1.2 minus 1.1 gives me 0.70 kilograms. So let's label that as well. 0.70 kilograms. Now, who could tell me what the very first thing we do with this is? You all know this. You were all thinking about it over the break. I know you were driving your cars, and then you were driving down the highway. Someone's merging onto the highway. The on-ramp is angled at about, say, 30 degrees to the highway. And I know what you're thinking. Every single time you see that, you're thinking, I don't like funny angles. I don't like funny angles. I got an angle of 30 degrees here. I don't like funny angles. Every time in any context that you see a funny angle, anytime, any context, you say to yourself, I don't like funny angles. You take it off to the side and you put it out of its misery and get rid of it. So let's draw it over here. We've got 30 degrees right here. We have an X and we have a Y. And our resultant here, our hypotenuse there is 100 meters per second. We're going to solve for the X component using a trig function. Some of you are more familiar with sine, cos, tan than others. Tell me whether it's sine or cos. Tell you it's not tan. It's not tan. Sine or cos for the X component there. Cos it is, yes, because look, we're looking for the adjacent side. We have the hypotenuse. X ends up being equal to 86 point something. 86.6025, thank you. And the Y component, we'd say sine for the Y component. Sine 30 degrees is equal to opposite over hypotenuse, and the Y component ends up being 50 meters per second. Let's box this off, because this is what makes this question different than what we were doing just before the break. So box it off to make it show that it's different. Now, see this 100 meters per second right here? See this? Dead to us. We never want to see that 100 meters per second again. Why? Because we replaced it with a 86 and a 50. In effect, what we have is not this anymore. In effect, we now have this, an 86.6025, and we have a 50 down this way. With an object number 2 that has a mass of 1.10 kilograms. Does that make sense what I just did there? You don't have to redraw like I just did if you don't want to, but sometimes maybe it's helpful. It's a reminder that that 100 meters per second is no good to us anymore, ever again. So we're going to pretend, in effect, that object number 2 wasn't going at 100 meters per second at 30 degrees. Rather, it went at 86, and it went at 50. Two separate velocities. Let's do our components here. X component. Let's say PI is equal to PF. Anybody know the initial momentum of this fireworks bundle before it explodes? 0, because it's just sitting on a table, right? 0 is equal to, well, there's 3 objects. For the first time, I think we've seen 3 objects in a question. That's no big deal. You get 2 objects, it's M1 V1F plus M2 V2F. If it's 3 objects, it's M1 V1F plus M2 V2F plus M3 V3F. Man, I wish the masses were the same. If the masses of all the fireworks pieces were the same, then I could do what? How would it make it easier? Not conceptually, but mathematically it would make it easier because I could cancel the masses out, right? Can't do that here though because they're not the same. All right. Let's see. 0 is equal to M1. Oh, wait a second. What's the momentum of object number 1? X-axis. Remember, x-axis is this, right? How much of that 120 meters per second is on the x-axis? What is it? None. None of it. The third territory of Canada, none of it is on the x-axis. All of it is on the y-axis. So we're going to say 0 momentum for that guy on the x-axis. M2 is 1.10 kilograms. What's V2F? What's V2F? Not 100, because that's gone now, right? Yep. Yep. 86.6025. M3 is 0.70 kilograms. V3F, we solve for that. We get a value for V3F for the x component of negative 136. 0.0896 meters per second. And make sure you can get that value. Okay, we've talked about this before, right? You can watch, a basketball superstar make some crazy move. You say, hey, I understand how he did that, or how she did that. And I could do it, but then when you go to try it, you can't do it. You have to practice it, right? You look at this and say, oh, I understand how he got 136. Well, you got to do it. You got to practice it in order to make sure that you can get 136 as well. Okay, am I done? I'm looking for the velocity. Didn't I just find it? No. Jade, what do I got to do? Yeah, I got to do the y component. So let's do that. Let's say for the y component, which is the up and down, right? The y component, the north-south. We're going to say, again, pi is equal to pf. 0 initial momentum equals m1 v1f, 3 objects, m2 v2f, plus m3 v3f. M1 is 120 kilograms. V1f. Tell me what V1F is. For the x component, it was 0, right? But now we're looking at the up and down. What's the y component of that 120? All of it, right? All of it. Not none of it. Here we've already used none of it. It's the fourth territory now. All of it. Okay. 120 meters per second plus 1.10 kilograms. That should have been 1.20, right? Yeah. 1.10 kilograms times, what's V2F? The up and down, object number 2. Up and down, object number 2. Emily, what is it? Yes. Not only is it 50, not 100, because the 100 is dead to us, it's negative 50 because it's going down, right? M3 is 0.70, is V3F. So what I want you to do is get this number, combine them, take it to the other side, divide by 0.70. And V3F works out to be 127, negative 127.1429. Make sure you can get that. If you can't, then make sure you let me know. Now comes the easy part. Now comes the physics 20 part. Really, it's the physics 20 part, but it's really based on math 10. So really, it's the math 10 part. This is a question that I guarantee you in another month, if not now, a grade 10 student, a decent grade 10 student could solve fairly easily. We've got 136 to the left. And we've got 127 down. We were looking for this. By the way, we knew that it was going to be to the left. We guessed down to the left. Were we right? Did we guess right? Yeah, because we know that it's left because the x component is negative. We know that it's down and left because the y component is negative as well. We solve for v here. Using the Pythagorean theorem, the a squared plus b squared is equal to c squared ends up giving me 1.9 times 10 to the 2 meters per second. And theta, we'll show you the work on this one just because some of you haven't used sine cos tan quite as much as others. Theta is the inverse tan function of opposite over adjacent. When you solve for theta, it works out to be 43 degrees. Now, can you tell me, is that 43 degrees? This is west, this is south. It's south and west, right? Is it south of west, or is it west of south? Where are we measuring the angle from? The west or the south, right? Yeah, we're measuring it from the west, but yet we're going south from the west, right? It's touching the west axis, but yet we're going south from the west. So instead of saying south from west, we'll call it south of west. 1.9 times 10 to the 2 meters per second at 43 degrees south of west. Had you drawn the y-axis, then the x-axis, you would have gotten 47 degrees. But it wouldn't have been south of west. It would have been west of south. Either one would be correct, right?